So let's go ahead and wrap up section 4.1, and we'll talk about end behavior of a polynomial. So here is our general formula. Whoops, I was not in pointer mode, sorry. So here is our general formula for a polynomial. Notice that this is of degree n. Okay. What is called end behavior? This just means what happens as x either goes to get bigger and bigger and bigger, or more and more negative. Okay. Essentially, the end behavior of a polynomial is controlled by the power function of its largest power. So if I had a polynomial that had a whole bunch of terms, and I want to know what does it do as x becomes enormous, is a million big? No. Is a trillion big? No. We're talking way, way bigger than that. Okay. Just as you keep plugging in bigger and bigger and ridiculously larger numbers, what happens to the graph is determined by the biggest power term in the polynomial. Okay. And we know if you have an even power with a positive leading term, we learned a couple videos ago that as x goes to infinity, the graph goes to infinity. But as x goes to minus infinity, the graph also goes to positive infinity. If you have an even power, and that's the only thing going on, then positive versus negative doesn't matter so much. But if you have a bunch of terms of smaller powers, so suppose you have an x squared, an x cubed, and x to the fourth, and then you have an x to the 10th. If you're plugging in really, really big numbers, then I have first power, second power, third power, fourth power, and 10th power. That 10th power is ridiculously larger than anything else. Okay? A big number times itself 10 times is going to be way bigger than a big number times itself 4 times. That's why, as x goes to infinity, it's really just that single largest power of x that's controlling what's going on. So if you had an even power and a positive coefficient, while it could do weird stuff in between, eventually it's going to go to infinity on both sides. If you had an even power and a negative leading coefficient, nothing changes very much. It just gets reflected to have to be going off to minus infinity on both sides. This is for even powers. So even powers, you do the same thing on both sides. If it's a positive coefficient, you go to infinity. If it's a negative coefficient, you go to minus infinity. And that's expressed on these two pictures on the left. An even power does the same thing to the left and the right. With a positive coefficient, positive leading coefficient, it goes to infinity. With a negative leading coefficient, it goes to minus infinity. Odd powers switch. So either you go to negative infinity and then positive infinity, and that's what happens for a positive coefficient. Negative to the left, positive to the right. But with a negative coefficient, it's reversed. Negative to the left, or sorry, positive to the left, negative to the right. So even powers, if that's the biggest power, your end behavior will do the same thing on both sides. And you can determine whether it's going to plus or minus infinity based on whether the leading coefficient is positive or negative. For odd powers, it does opposite things on both sides. If your leading coefficient is positive, you are negative on the left and positive on the right. And if your leading coefficient is negative, you're positive on the left and negative on the right. Okay, so let's look at some examples. Which of these could possibly be the graph of x to the 5th, ax cubed, bx squared, negative 2x plus 3, where a is positive and b is positive? Well, it's a degree 5 polynomial, so how many turning points could it possibly have? At most, 4, which means this one's out. That has way too many turning points. That cannot be the graph of a degree 5 polynomial. What else can you say? Think about end behavior. So its leading term is x to the 5th times what? Times 1. That's positive. So I have an odd degree, which means it's going to do opposite things on both sides. Well, that doesn't narrow it down. But the leading coefficient is positive, it's 1, and that means my end behavior needs to be negative on the left and positive on the right, which means this one's not possible. Okay. Now, how can I distinguish between these two examples? It's kind of a matter of, was it drawn reasonably well? Okay, so in this specific example, we can, however, plug in and ask, what is f of 0? And we get out 3, which means this makes sense and this doesn't. So generally, I wouldn't rely on how well someone can draw a picture, but what's positive versus what's negative, that's something you can extract. So this slide is just reiterating all those points we just made. I just wanted to do it while looking at the pictures. So combining turning points and end behavior, we eliminated a couple, and then just using the fact that the intercept has to be positive, we eliminated the last one. Okay, so it's got to be this one. If it's any of them, it has to be this one. Notice also, this is not a way I would like to phrase a problem because the book gave you this information which never came into play. It was not relevant at all. Okay, find a polynomial whose graph is shown. So now we can assume that the labeled points are accurate. Otherwise, positive versus negative you can distinguish, and turning points you can distinguish. But notice, the intercepts have been given, and these are the only intercepts. So use that somehow. So if -1 is a root, x plus 1 has to be a factor. 1 is a root, which means x minus 1 has to be a factor. And 2 is a root, which means x minus 2 has to be a factor. I could multiply by anything I want. Let me write that with a little bit more space. Anything times x plus 1, x minus 1, x minus 2. However, think about end behavior. Is it opposite on both sides or the same on both sides? It's the same on both sides. Okay, it's going up in both directions. That means this can't be the end of it, because what we have written now is a degree 3 polynomial, and that would have opposite end behavior on both sides. So we can't introduce any other roots, so I can't introduce any other factors. What I can do is I can change the multiplicity, for example, like this. Okay, now I have not introduced any new roots, but I have changed the degree. If I were to expand all of this out, this term here would give me an x squared times an x times an x. Overall, this is now a degree 4 polynomial, which now matches the end behavior, that it does the same thing on both sides. It also matches the fact that there are 3 turning points. Okay. So, as said, here are the factors we have. There are 3 turning points, so the degree has to be 4. Also, the end behavior tells you that the degree has to be even, so it couldn't have been 3. We didn't explicitly say this on a previous slide, so I didn't mention it. But when the multiplicity of a root, so I apologize for only bringing this up now, it just wasn't on an earlier slide. If the multiplicity of a root is even, then the graph does something like this. If the multiplicity of a root is odd, then the graph actually crosses at that root. So if the multiplicity is odd, you get a crossing. If the multiplicity is even, you get no crossing. Since this root didn't have a crossing, okay, when I wrote the function f of x is something times x plus 1 times x minus 1 times x minus 2, we said that can't be the end of it. The degree is wrong. Also, because the graph doesn't cross the axis here, the degree of that root has to be even, which is why I went ahead and increased that one to be of degree 2. These do cross, which means that their multiplicity is odd. So I could actually come through and say something like x minus 1 cubed, x minus 2 to the 11th. Okay, this is unlikely to be accurate because my degree now is here I get an x squared, here I get an x cubed, here I get an x to the 11th. Overall, I'm going to get an x to the 16th, which means I could have up to 15 turning points. I'm not guaranteed to. I can't guarantee this graph couldn't possibly be this function, but usually you get about as many turning points as you're allowed. So if I tried to graph this, I would reasonably expect to probably have 15 turning points. And since this graph only has 3, we're probably only looking at a degree 4 polynomial. So once I accomplished that with this, I figured I was probably done. Also, that coefficient out in front had better be positive because my end behavior is positive in both directions. And that matches up with a degree 4 polynomial with a positive coefficient out in front. Okay. So just to talk through that again, we could have put a multiplicity of 2 on this root, and then find the leading coefficient has to be positive. Well, our intercept was actually labeled, I didn't notice that, which could allow us to find exactly what that coefficient is. I do want to stress that based on the information that the book has given us, this is wrong. This has to be the root with even multiplicity, not the other one. I think this is just a typo and not a genuine mistake. Okay, so again, there we are. And they forgot to put the square in it at all, that job book. So if you want, you should be able to graph this and get exactly that out. Okay, so that ends section 4.1. We learned about polynomials, what the degree of a polynomial is, what the word multiplicity means when it comes to roots, and some basics of how to graph them. If I just threw any polynomial at you, you probably wouldn't be able to graph it, but don't worry, we'll learn some more techniques later.